Hey guys, so in today's lecture, we'll see various examples of design of springs. So how we can design a spring for various shear stress. So for various type of material. So let's see example so it will be more clear. So helical spring is made of a wire diameter of 6 mm. So here small d is given as 6 mm and has an outside diameter of 75 mm. So capital D is given as 75 mm. So if the permissible shear stress is 350 megapixel Pascal, so that is tau is given as 350 and modulus of rigidity is 84 kilonewton per mm square. So G is given as 84 megapascal. Sorry, gigapascal. So find the axial load which the spring can carry and deflection per active turn. So two things we need to find here. So first we need to find the axial load. So that is W, and second is deflection per active turn. So deflection is delta, per active turn is N. So W and delta by N we have to find. So now this we can solve in two cases. So first case will be that neglecting the effect of curvature. So if we are neglecting the effect of curvature effect. So if we neglect the effect of curvature, then the shear stress factor K will be just Ks, that is 1 plus 1 by 2C, which will be equal to, now what is C? C is capital D by small d. So as we have capital D as 75 mm and small d is 6 mm, so C will be equal to 11.5 mm. So from this we can find Ks. So Ks is equal to 1.043. Now what is the mean diameter of the spring? So mean diameter D will be equal to D0 minus D. So that is outside diameter minus the diameter of the coil. So now shear stress tau is given, as we know the formula is, that is tau is equal to Ks, that is shear stress factor, into 8WD divided by pi d cube. So we will use here Ks, that is 1.043 into 8WD. Now tau we have, so tau is 350, Ks we have 1.043 into 8 into W. W we are interested in finding, okay, actual load, into capital D. D we are taking as mean diameter D0 minus D, which is equal to 75 minus 6, which is equal to 69. So it is 69 divided by pi d cube. So it is equal to pi, it is 3.14 into d cube. D cube is 6 cube. So here we will get W is equal to 412.7 Newton. So W we have found. Now deflection delta. So we know that the deflection is 8W d cube N divided by G d raised to 4. So we are interested in finding delta by N. So N here if we divide, so delta by N will be equal to 8 into 412 0.7 W we have found into d cube, that is 69 cube upon 84. G modulus of rigidity is given 84 into 10 raised to 3 into 6 raised to 4. So if we find, it will be equal to 9.96 mm. So here we have neglected the effect of curvature. Now if we are going to consider the effect of curvature, so in that case what we have to do? So if we considering curvature effect, if we consider the curvature effect, so we will have k is equal to 4c minus 1 divided by 4c minus 4 plus 0.615 divided by c. So in this case, if we consider the curvature effect, so the Wahl stress factor, instead of the shear stress factor, we use Wahl stress factor. So this will be equal to 1.123. So there we got 1.043, and so we'll use also the maximum shear stress induced in the wire tau will be equal to same k into 8w 8wd divided by pi dq. So the formula is same, just k we have changed here. There we used ks and here k, so k will just change. So same procedure we will follow. The same formula we will use, and so we'll substitute in the equation. So we'll get we will get w is equal to 383.4 newton. So there we got 412.7, here we got 383. Similarly, delta equation will be also same, 8w d cube n by gd raised to 4. Same equation, if we will substitute, the only w value will change here. So we'll get delta by n as 9.26 mm. So there we got 9.96 mm. So there is a difference between if we consider curvature and if we neglect the curvature effect. So as there is no major difference, if there is a major difference, we need to consider the curvature effect. Now we will see another another example. So let's see another example. So here, design a spring for a balance to measure 0 to 1000 newton. So you need to design a spring balance to 0 to 1000 newton, 1 kilonewton, or a scale of length of 80 mm. W is given 1000 newton, length is given, so that is deflection. So deflection is 80 mm. So the spring maximum deflection is 80 mm. The spring is to be enclosed in a casing of 25 mm diameter. The approximate number of turns is 30. So small n is given 30. Modulus of rigidity is 85 kN per mm square. And mean diameter, that is the outside diameter should be less than 25 mm is given. So d0, so d0 should be less than 25 mm because the casing is of 25 mm diameter. Also calculate the shear stress induced. So let d is equal to mean diameter, small d is spring diameter. So let's calculate uh, delta by n. Sorry, delta is equal to 8 wc cube n by gd. So with this equation we'll find small d. So delta we have 80 mm, 80 mm, 8 into w. W we have 1000 Newton, 1000 Newton. C we are keeping as C because we don't have C, into N. N we have small n is 30. G we have, that is 85, into 10 raised to 3. And D, small d, D we don't have. So C cube by D we don't have, so we'll make this as a subject. So we'll get C cube by D is equal to 28.3. C cube by D will be equal to 28.3. So now here there are two unknowns, that is capital D and small d, and we have one equation, so this cannot be solved, but we have one constraint for capital D, so it should be less than 25 mm. So 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 we can do here is that we have to assume the diameter, any one diameter, in order to solve. So we are assuming D is equal to 4 mm. So we will see if this assumption is correct or wrong. So if we take small d is equal to 4 mm, so from this equation, so we'll get capital D is equal to 19.36 mm. Now D0, outer diameter, is equal to D plus D, as we know that. So it will be equal to 19.36 plus 4 mm, so which is equal to 23.36 mm. It is 3.36 mm. So which is less than 25 mm. So our assumption is correct. So therefore small d is correct. So we can design in this way. Now we have to find another thing, that is maximum shear stress induced. So shear stress formula we know, that is tau k 8wc divided by pi d square. Or if we don't write c, so then it will be k into 8wd divided by pi d cube. So here k is wall stress vector, so we are considering the curvature effect, so that is equal to 4c minus 1 divided by 4c minus 4 plus 0.615 divided by c. So if we solve this equation, so c we have, that is capital D upon small d, so if we solve this equation it will be 1.322. So in shear stress formula, now K we have, 8W we have, that is 1 kilonewton, C we have, and D we have. So if we find tau shear stress, it will be 1018. So 1018.2 megapascal. So this is the shear stress induced. So similar type of examples will come in exam based on these formulas only. Now we'll see smaller theories which may or may not be asked in exam, but it is very much useful. So first is spring in series. Spring in series. So suppose this is the weight W and here spring K1, K2. So this is K1 and this is K2. So this is spring number 1 and this is spring number 2. Suppose there are two springs having stiffness K1 and stiffness K2. and weight W, load carried by the spring W. Now there will be deflection of let's say delta 1 is the deflection of spring 1 and delta 2 is the deflection of spring 2. So K1 will be equal to W by delta 1 and K2 will be equal to W by delta 2. So the total deflection of the spring will be equal to delta is equal to delta 1 plus delta 2. So W by K is equal to W by K1 plus W by K2. So W gets cancel out. So 1 upon K is equal to 1 upon K1 plus 1 upon K2, where K is equal to combined stiffness of the stiffness in springs. So as we know that this series and parallel equations we have seen at various times, like in electrical circuits, that resistors in series, capacitance in series, inductors in series and parallel. So what will be the equations? So here in resistance, generally it is the addition, and but here it is the reverse of the resistance. So in series we are getting the formula 1 upon K is equal to 1 upon Q1 plus 1 upon K2. Now, so the reverse will be true for parallel, that is K1 plus K2. But then also we'll see. So second is spring in parallel. So suppose these are the two springs, and here the weight W is load W is applied. Here having stiffness K1 and K2. So W load carried by the springs. So now a little consideration will show that when springs are connected in parallel, then the total deflection produced by the springs is same as the deflection of the individual springs. So that is delta will be equal to delta 1 is equal to delta 2. So as we know the formula, so the total weight will be divided by the 2, that is W is equal to W1 plus W2. So weight will be divided by the springs, that how much we are carrying. So W is equal to delta K is equal to delta K1 plus delta K2. So delta will get cancelled out. So K is equal to K1 plus K2, where K is the combined stiffness of the spring and delta is the deflection produced. So this is the springs in parallel. So similar type of examples can be asked, that if there are two springs in parallels having stiffness K1 and K2, so find the combined stiffness. So if you know the formula, then you can find the combined stiffness easily. So this is a very small topic for springs in series and parallel. So in the next lecture we'll see, so what we'll see, we'll see concentric uh, springs and leaf spring. So leaf spring is a very important topic asked in exam, and also very big topic. So that we'll see in the next lecture. So in this lecture today we have seen two examples and two theory, that is one theory, springs in series 1 and springs in parallel, two theories and two examples. So I hope you understood. So let's see in the next lecture. So thank you very much.